We propose a new framework for Bayesian Model Predictive Control, SV-MPC, for optimizing over complex multimodal control policies. We formulate model predictive control as a variational inference problem over a sequence of decision parameters. Given a family of policies and a dynamics model, these parameters define distributions over predicted state and control trajectories, along with resulting costs. We can then minimize the KL divergence between a proposal distribution and the target posterior over the parameters given trajectory costs. The resulting optimized distribution is then used to generate a parameter sequence for the next MPC iteration. In our approach, we employ Stein variational gradient descent to optimize the variational objective. Here, the posterior is approximated using a set of particles over the parameter space. Functional gradient descent is performed iteratively to update the proposal distribution. The particles evolve according to a gradient flow where particle velocities are governed by maximizing repulsive terms. This drives particles towards higher probability regions while pushing them apart and promoting particle diversity. This non-parametric representation is flexible and can capture complex multimodal posterior distributions. Building on this idea, we introduce Stein Variational Model Predictive Control, or SV-MPC, where each particle represents a sequence of parameters. These may parameterize a policy distribution or directly represent sequences of control actions. Scaling to high-dimensional regimes is made possible by using factorized kernels, which incorporate local and temporal structure in the embedding. We first test our approach on a planar navigation task. We compare to MPPI, a common sampling-based MPC algorithm. Here, SV-MPC can be seen as a distribution over MPC controllers. Each color indicates a set of rollout trajectories generated by a single particle in the distribution. The representation allows SV-MPC to capture narrow passages and quickly get to the goal. Next, we make a similar comparison on a high-dimensional reaching task, performing joint velocity control on a 7-degree of freedom manipulator. The task is to move the grasp point of the end effector, indicated by the green dot, to the red target while avoiding obstacles. Rollout samples are generated in parallel using the NVIDIA Isaac Gym library, a GPU-accelerated simulation suite. We first compare against an MPPI baseline. As can be seen, the unimodal distribution converges to a poor local optimum, and the robot gets stuck between two obstacles. The multimodal distribution of SV-MPC can resolve multiple local optima simultaneously, allowing the robot to find a low-cost trajectory around the obstacles and reach the goal. We compare trajectory traces of end effector positions for SV-MPC, MPPI, and CEM over multiple trials with fixed sample sizes. Despite fewer samples being available for gradient estimation, SV-MPC typically finds lower cost trajectories and manages to reach the goal. The SV-MPC framework can also be applied to trajectory optimization, where particles are defined over control input sequences. The objective is assumed to be fully differentiable, allowing gradients to be evaluated by backpropagating through costs and trajectory dynamics. We can also leverage informed priors on control sequences. These can incorporate Markovian dependencies on solutions, such as smoothness. We test this approach on a planar motion planning problem. The robot must find a sequence of velocity commands to produce a feasible low-cost trajectory to the goal. For a randomly initialized set of control particles, we optimize directly over a distribution of 2D velocities, shown in the lower right, where each trajectory results from a single particle. The distribution quickly converges to a set of low-cost trajectories. However, in order to find a local optimum, we refine the solutions by performing stochastic gradient descent optimization on individual particles. We finally obtain the global optimum solution indicated by the green trajectory. Thank you for watching.